We are going to cover hypothesis testing in Julia. We will be using a MLB dataset to practice using the hypothesis test functions. Before you begin to code, you must download the hypothesis test package and then state using hypothesis tests. The functions that are included in the hypothesis test package are one sample t-test, confidence interval, p-value, and a two-sample t-test for equal variance and unequal variance. The default alpha is 0.05 and tail is both. There are assumptions that must be met prior to testing your hypothesis. First, your data must be normally distributed. Variances of your samples must be equal for the two sample tests. Your data should have a linear relationship, and your outcomes must be independent to one another. If you have a small sample size, you will have to check if your data follows a normal distribution. You can use the QQ-norm function and fit a QQ line in red to display the normal line. If your data has a large sample size, by the central limit theorem, you can assume your data follows the normal distribution. For the one-sample t-test, the null hypothesis is that the population mean equals 0. In Julia, you cannot change the value of your population mean, so your null value will always be 0. Our MLB dataset will not be an ideal dataset for the one-sample t-test, so we will have to create our own sample using a random number generator. We will get 100 random numbers that are normally distributed. Then, we will use the one sample t-test function to test if the average of those random numbers are 0. Note that by default our alpha equals 0.05. If you are interested in knowing only the confidence interval, you would use the confint function. The default alpha is 0.05 and the default tail is both, but you can change these. If you are interested in knowing only the p-value, you would use the p-value function. The default tail is both. The equal variance t-test is for a two-sample t-test, assuming the variances of both samples are equal. In our baseball example, one sample will be the average home runs of the National League, and the other sample will be the average home runs of the American League. The reason we are testing this is because the American League have pinch hitters, meaning that they have hitters who replace the pitchers in the batting lineup. Whereas in the National League, pitchers are included in the batting lineup. Our null hypothesis for this test, assuming the variances for both samples are equal, is that the average home runs in the National League is equivalent to the average home runs of the American League. In order to get the variable home run for each league, we will create a subset for each league. Then, we will use the equal variance t-test function to test it. The unequal variance t-test is a two-sample t-test assuming that the variances of both samples are not equal. The null hypothesis is the same as for the equal variance t-test. The function used will be the unequal variance t-test. In our second example, we will be testing the differences in stolen bases by league. Again, we will create a subset showing the number of stolen bases by league. Then, we will use the equal variance t-test. Before we begin, you have to make sure you downloaded all the packages you will need beforehand. For our example, you will need the data frames, stat plots, hypothesis tests, and distributions packages. Then remember to state that you are using those packages. As mentioned before, we will conduct a one-sample t-test using a random number generator. Using the function rand_n, 100 numbers will be generated with a normal distribution, and we will call that vector x. Then, we can run the one-sample t-test. The test includes the parameter of interest, which is the mean, what the value under the null is, the point estimate, and a 95% confidence interval. Here, the confidence interval is -0.14 and 0.25. So we are 95% certain that the average is at the lowest -0.14 and at the highest 0.25. Under the test summary section, Julia actually gives you the conclusion of the test, which in our case is to fail to reject the null. The p-value calculated is 0.55. Under the details section, it lists number of observations, the t-statistic, degrees of freedom, and the standard error. The confint function only displays the confidence interval of your test. We can run the confident function for our one sample test to double check that that was the confidence interval we got when doing the one sample test. The confident function gives us negative 0.14 and 0.25, which is the same as the t-test. You can also change the alpha values and the tail to fit your interest. When tail equals right, you will get the upper bound to be infinity, and when tail equals left, the lower bound will be negative infinity. The p-value function will only display the p-value of your test. We will run the function to double check that it is the same value as our t-test. The p-value function gives us 0.55, which is the same as our one sample test. You can also change the tail to right or left. Now we will use our baseball dataset to do a two-sample t-test. First, we will call in our dataset using the read table function and call it MLB. There are 134 observations with 21 columns in our dataset MLB. Then, we will create our subset called National. The subset includes all observations that list NL in the league column and will display the home run column. National has 65 observations and includes one column for home runs. We can do the same thing for the American League, and it shows to have 69 observations and one column as well. Because we have a large sample size, we can assume the data follows a normal distribution with the central limit theory. However, we will use a QQ plot to help us visualize how our data is distributed. First, we will create a vector, vec_nhr. This will transform our National League home run data points from an array to a vector. Then, we will use the QQ_norm function to plot the points vec_nhr and fit it with a red normal line using the QQ_line function. As you can see, the data points follow a normal trend. Now you can use the equal variance t-test to see if the average home runs in the National League and the American League are the same, assuming the variances are equal. The parameter of interest here is the mean difference. The 95% confidence interval is negative 6.1 and 0.9. The American League can have a higher home run average by 6, or the National League can have a higher home run average by 0.9. 0 is included in the confidence interval and the p-value is 0.15, so the result is to fail to reject the null. We will also run the unequal variance t-test. The null hypothesis will be the same, and the values do not change by much, assuming the variances of both samples are unequal. The conclusion for both tests is that it failed to reject the null. Because we failed to reject the null in both the equal and unequal t-test, we can say that the average home runs in the National League and the American League are the same. So even when the pitchers are being switched out in the batting lineup in the American League, the average home runs are equal to the average home runs in the National League. We can do another test to see if there is a difference in stolen bases between the National and American League. We will create a subset for both leagues again, and then run the equal variance t-test on both subsets. The 95% confidence interval is 0.3 and 7.2, with a p-value of 0.03. The conclusion of this test is to reject the null. We are 95% confident that the National League has between 0.3 to 7.2 more stolen bases than the American League. The hypothesis test package in Julia is sufficient for simple tests, but there are still changes needed to be made to switch any R levers to Julia. Unlike R, Julia does not have a variance test to see if we can assume equal or unequal variance. Also, though we can manipulate the alpha value for the confidence interval and the p-value, your one sample and two sample t-tests are all run using the alpha value 0.05.